Alrighty, so we're going to start chapter 6 in this video, talking about the normal distribution. We'll go ahead and just preference this. Normal distribution is pretty much the baseline of your statistics from here on out. So everything's going to kind of go around normal distribution. Just to give you an idea of what normal distribution is like the bell curve that you've always heard of. That is pretty much where normal distribution kind of comes into play. And we can pull a lot of information from that if we assume or we're told that something is a normal distribution. All right, so let's get into these notes. So a random variable can be either discrete or continuous. So a little bit review of what we've seen so far. Continuous variables such as heights of adults and body temperatures of rats can assume all values between any two given values of the variables. Although no variable fits a normal distribution perfectly, the normal distribution can be used to describe many variables since the deviation from a normal distribution are small. So standard deviation plays a big part in normal distribution as well. So in 6.1, that's what we'll look at in this video, talking about normal distributions. Our first objective is just to identify the properties of a normal distribution. Sometimes they'll just tell you it is, and then sometimes it won't. So we have to look at our characteristics and go, all right, is this a normal distribution or not? Because as we progress in this semester, you'll learn other types of distributions as well. We've already seen binomial distribution, but you'll see other distributions, and you get to a point where you start having to start to identify which one is this one so I know which formulas to use. So the definition of normal distribution is if a random variable has a probability distribution whose graph is continuous, bell-shaped, and symmetric, it is called the normal distribution. Right? The graph is also called a normal distribution curve. All right, so mathematical equations for normal distribution is as follows. So y equals e raised to the negative of x minus mu squared divided by 2 times the variance, all divided by the standard deviation times the square root of 2 pi, where e is equal to 2.718, pi is equal to 3.14. Again, mu is the population mean, and sigma, lowercase sigma, is the population standard deviation. Just an FYI. That is a formula that helped us calculate the things of a normal distribution. You will never have to use that, right? So the shape and position of the normal distribution curve depend on the parameters of the population mean and the population standard deviation. So these two characteristics can tell us a lot about our normal distribution. All right, so make sure you have that. And let's look at some curves. All right, so this is what a bell curve of normal distribution is. So you can see that the average is 0 and it's directly in the middle. And you can see in this yellow here, a standard deviation of 1, standard deviation of 2 is a little more spaced out. So you can see here's 1, here's 2. So same means, just different type of standard deviation. It just gets more spread out. So the closer standard deviation is, the more straight up and down that is. The larger your standard deviation, the more spread out your that is, like your variance of your data. And then you can kind of see here, this is again, the bell curve is still the same size with the same standard deviation, just the mean has shifted down on the x-axis. So instead of 0, now it's at 2, but still the same shape. So when the population means are the same, but the population standard deviations are different, the curve with the larger population standard deviation is more spread out, as you could see in that first diagram. When the population standard deviations are the same, but the means are different, the curves have the same shape, but are centered at different points along the x-axis, as you can see in the part B graph. All right, so I'm going to scroll this up because there's a lot of properties. So summary of the properties of theoretical normal distribution. Again, theoretical just means what should happen, and then we can make a normal distribution out of it, versus if we actually did some trials, something different could happen. But if we did an infinite amount of trials, it would all go back to the theoretical. All right, so a normal distribution curve, again, is bell-shaped. The mean, median, and mode are located at the center of the distribution. They're all equal and they're all the same value. The normal distribution curve has exactly one mode, and it's going to be whatever the mean is. The normal distribution curve is symmetric about the mean. So everything is even on both sides. The normal distribution curve is continuous, having no gaps or holes for all values of the independent variable. So there is a place for a value at every spot. The curve approaches, this is a big one, people just assume it goes straight to zero, but it approaches but does not meet the x-axis, just getting increasingly close while never touching the x-axis. So what you'll see in this data is this will be a certain percentage, and they'll get a little bit more percentage, and they'll get a little bit more, and it'll just turn into like 99.999% of the data and keep going, but never be exactly 100. However, if you did want to know what the total area under a normal distribution curve is, it is going to be 1, because it's going to tell us the percentage of our data that's underneath it. So 99.99% is about 1. All right. Let me get to the other facts. So the area under, see if I can go one click. Nope, it won't let me. There you go. The area under the part of the normal distribution that lies within 1 standard deviation of the mean is approximately 68% of your data. So if this is my mean, and this is plus or minus 1 standard deviation, it's about 34.13% on both sides. We'll just round it to 68%. So 68% of my data, you can see it right here, is within plus or minus 1 standard deviation. Within 2 standard deviations, the mean, it's approximately 95% of my data. So again, plus or minus 2, I can see that this right here will contain 95% of my data. And then within 3 standard deviations, approximately 99.7%. So that's this part right here. So 99.7% of my data will fall under this curve. And you can kind of see there's still a point. This says 13%, but we'll round about and say 0.15% on each side that will be more or less like your outliers. By the way, this is also known as the empirical rule. So we will assume such things. And it's basically that formula I showed you earlier. That's how they're calculating this. You do not have to know that. What you do have to know is 1 standard deviation is 60, 2 standard deviation is 95, and 3 standard deviation is 99.7. And then knowing that if you half each one of those, you will get a certain different percentage on the left or the right side of your curve. That will come into play later when we kind of introduce what we call z-scores. This is kind of getting ahead of the subject, but that will eventually show up. And there you go. So there's your 99.7. All right, in our second objective, we're going to identify distributions as symmetric or skewed. So the normal distribution is symmetric about the mean. That is, the data is evenly distributed about the mean when the majority of the data values fall either to the left or right of the mean. The distribution is skewed. So if we have more data towards either the left or right, it is considered to be skewed. When the majority of the data is to the right of the mean, the distribution is called negatively skewed. So again, if more of the data falls on the right, it is a negatively skewed data. Or what we also call left skewed. If the mean is less or to the left of the mean, the distribution, so if the mean is less than or to the left of the median, the middle number, so when the majority of the data is to the left of the mean, the distribution is positively skewed or right skewed. The mean is greater than or to the right of the median. The tail of the curve indicates the direction of the skewness. So right is positive, left is negative. So if you see a tail on the right, then you know it's going to be a positively skewed. If you see a tail on the left, then you know it's going to be negatively skewed. So let's look at pictures so that you can see what that means. So in these pictures, you can see here is a perfectly normal distribution where everything is even, mean, median, and mode. As you can see here, here is the mean. Now everything is to the right of the mean. So that means everything's, the median's on the right, the mode's on the right, and most of my data is on the right. So therefore, this will be a negatively skewed data, or also known as left skewed. And we can see that because here is the tail. So a left skewed data. Over here, you see here's the mean. Now the median and mode is on the left. All my data is on the left, so it's positively skewed. And I have a tail over here, so this is now a right skewed. And basically what that's doing is I have my data here, but whatever these numbers are so large, it's pulling my mean this direction. So as you can see here, my mean is being pulled this direction, even though most of my data should be here. All right, in our third objective here, we're going to find the area under the standard normal distribution given various z values. A z value is just how many standard deviations from the mean you are, and then you can calculate what the percentage of that data should be. So definition, standard normal distribution is a normal distribution. Go figure. With a mean of 0 and a standard deviation of 1. So a standard normal one, the mean would be 0, and then standard deviation on each side will be 1. So this would be 1, this would be -1. This is 2, this is -2. So basically what you can do is you can take any normal distribution curve that you have, and you can find the answers out using the standard normal to kind of figure out how much percentage of the data is between whatever data you are. Again, here's the formula for the standard normal distribution. Again, we'll never use it, but if you're curious, that is what you can use. All right, so we see that all normally distributed variables can be transformed into the, well, that's exactly what I just said, into the standard normally distributed variables. By using the formula for the standard score. So this again is called a z-score. And if you had a certain value, you could subtract it from the mean and then divide it by the standard deviation, giving you this formula here. You'll be using this formula a lot. So do make sure you have it on hand because this is how you can find the z-score. And what the z-score again tells you is where are you located on the curve. And then from there, we can then determine what percentage of the data is above or below said value. So this standard score, also known as a z-score, again, is the number of standard deviation that a particular sample value is from the mean. Table E in Appendix A will be huge for you, so make sure you have that marked in your book or flagged it in the ALEKS program. Again, I do have it where the formula should pop up as an option for you because you'll be using this a lot. But what it does, it gives you the area to about 4 decimal places under the standard normal curve for each z value from negative 3.49 to 3.49. Technology can also be used to find the area under the standard normal distribution curve as well. But with these formulas, it's pretty quick on how you can get the answer using the chart. Without the chart, definitely going to need the calculator. So let's talk about how to find area under the standard normal distribution curve. So step one, you want to draw the normal distribution curve, shade the area under consideration. So maybe you want to know what is -1 standard deviations or less. Step two, choose the appropriate type of problem and either use table E in Appendix A or use your technology to find it. We're going to be using Appendix A. That's what I'll hyper focus on. All right, so to find the so-called area, so the area under the standard normal distribution curve to the left of a z value, simply just find the z value in the table E Appendix A and then use the area given. So let's see. I need Appendix A. So let me take a moment and go find that. Best thing I'm gonna be able to do is get to the ebook. Not got my document camera with me. And I did finally get a new edition of this book, which I did not know at first. And it looks like it's exactly the same. I think you have new examples, but the knowledge is all the same, which makes me a lot happier. All right, I think I got to it. Let me get to the top of it. All right. So you already have your notes in front of you. So I'm just going to switch gears over here so you can kind of see it. So this is how you use the chart. So this is the table E Appendix A. cumulative score, right? So what you have here is this is the z-score. This is the second decimal, or the hundredth place, and then this is the whole number point, the tenths place, and then you figure out what z-score you have, and then you go, and then that's the area. So for instance, looking at that table again, so I'm just going to call it A, B, and C. So we'll call A. A said find the area to the left of 1.32. All right, so to do that, I need to go to positive 1.234, 1.32, sorry. So this is, it starts in negatives. Oh no, I gotta remember now. This is 0 then 1, okay. All right, so here we go. So here is 1.3, so there's 1.3, and then I go to 2. So this is 0, 1, 2. So there's my answer right there. So if I'm looking for the area under the curve to the left of 1.32, the answer then is, where do you go? 0.9066. That just means that pretty much 90.66% of your data should fall from to the left of a z-score of 1.32. And a z-score, remember, is 1.32 standard deviations from the mean. 90.66% of my data should fall into that. All right, so that's basically how that's calculated. If you look at B, it says now the area under the standard normal distribution curve to the right side of the z value. To do this, you need to find it on this chart and then take 1 from it. And what you're doing is you're taking all, so let's just graph it real quick. So in this one here, this is, let's approximately say this is 1.32, right? I'm looking for all of that. That's why it's such a large number. In this case, I'm asked to find everything to the right of negative 0.67. So here's about negative 0.67, but this time I'm looking for the right. So the value it's going to give me, it's a really low number, so I have to do 1 minus whatever that value is so I can get everything to the right, right? So let's look for this value, which is negative 0.67. So we got to go up, looking for 0.6. All right, I found 0.6. And then so 0, 1, 2, 3, 4, 5, 6, 7. So that's 0.2514. So what that number here is this percentage here. 25% of my data should be to the left of this. But if I want the right of this, I need to subtract 1 minus 0.2514. And when I do that, I'll get 0.7486. That would be the area to the right of negative 0.67. Now, if I look at part C, the area under a standard normal distribution curve between two z values, you'll find both z values and then subtract the corresponding area. It's always going to be whichever the largest z-score is minus the smallest one. That will give you the area in between. So basically what's happening on this one, I'm going to draw a little bit bigger and then do the math underneath. You are given 1.45. Why is that negative positive? That's positive. So here's 1.45. And then you're given 2.32. So give or take, we'll say 2.32. You are asked to find the area in between here. So you need to find this area first and subtract it from this area. By finding this area, you will find all of this. And then if you subtract from this area, it'll deduct this part, leaving you with this little section here. So I'm going to first start off with 2.32, and then I'll subtract it from the 1.45. I won't actually do this to this number. I'm actually going to go find it, but I'm just trying to show you mathematically what's going on. All right, so I need to scroll down. So 2.32. So 2.3012 is 9898 minus 1.45. There you go. There's 1.4 right here. And then 0, 1, 2, 3, 4, 5. So that's 0.9265. You could also make a note that you can't have a negative. But I'll take these two values here, and when I subtract it, I'll get 0.0633. That would be the area right here. So 6.33% of my data would fall between 1.45 standard deviations from the mean and 2.32 standard deviations from the mean. So that's how z-score can work, and that's how you use Table E Appendix A. This right here is what you're pretty much going to be using the rest of the semester. So again, have it marked, have it available for all lectures, homeworks, and tests. All right, let's look at some more examples. All right, so that's your table. Again, I need this table still out to show you. So again, this is still in your notes. I'm just going to go to example 6.1. Find the areas between the two given values. First one says between z equals 0 and z equals negative 0.32. All right, so this one's bigger, and this one's actually a lot easier. 0 is always going to be 0.5. 0 means that is dead center of the mean. So the answer of that should be 50% of the data should fall to the left and to the right of the mean. So if you're 0 standard deviations away, you're on the mean. So all I really got to do is figure out where negative 0.32 is, and then I can subtract it. So negative 0.3, there it is right there. So here's negative 0.3012, that's 0.3745, 0.3745. When I take that, I actually get 0.1255. So again, that means that 12.55% of my data should fall between negative 0.32 standard deviations and 0 standard deviations. All right, so this is part A. Part B says to the right of 1.23. All right, here's 1.20123. So here's that number right there, 0.897, 0.8907. But if I want to the right of the data, I have to do 1 minus. So I do 1 minus that, and I come out with 0.1093. So that means that 10.93% of my data will fall on the right of 1.3123 standard deviations. All right, let's look at part C. To the left of negative 1.03. So I have to scroll up. So that's going to be negative 1.0123. So that's 0.15. I got lost. Where are we at? Negative 1.03. Negative 1.012. There you go. 515. All right, this time it said to the left. So whatever to the number I get in the chart is my answer when it says to the left. All right, let's look at D. All right, this one says between negative 2.15. So this is z equals negative 2.15 and z equals 0.97. 0.97 is a bigger number. So that means I'm going to do that one first. So 0.97. So 0, 1, 2, 3, 4, 5, 6, 7. That's 0.8340. So now I'm going to go look for negative 2.15. So there's negative 2.1, 0, 1, 2, 3, 4, 5. So that's going to be 0.158, 0.158. And when I take these two numbers, subtract them, I find I get 0.8182. So that tells me that 81.82% of my data will fall between negative 2.15 standard deviations and 0.97 standard deviations. All right? So that's how you do example 6.1. So let me jump back to the notes. All right, so we did that together. We've done this one together as well. So let's look at example 2. We want to find the probabilities for regions between two z values, and we're going to use this probability here. All right, when it's presented this way, it's exactly the same thing. You're just going to find the z-score of this guy and then subtract it from the standard, the z-score from this guy. All right, so if I look on my thing, 0.92, that would be 0.8212. And then if I subtract 0, which I already know is 0.5, I would get 0.3212. So what this is, when you're trying to find the probability of regions, you're basically saying, all right, if I want to find something that will fall between 0 and 0.92 z-score, then I have a 32.12% chance that I would grab one of those samples. If I want something less than 2.77, all I have to do is go find the standard deviation or the z-score of 2.77, which when you do that comes out to 0.9972, and then that's my answer because this is to the left of my my z-score, and therefore there's my data. If I want the right, I need to do 1 minus whatever my z-score of 1.12 is, which when you go, it looks like it's 0.8686. Therefore, that would be 0.1314. So again, if I want something greater than 1.12 z-score, then that would be a 13.14% probability of that happening. And again, you want to do this one first, 1.56, then go find the negative 1.2. 1.56 is approximately 0.9406 minus, now go find negative 1.20, and that is going to be 0.1151. Subtract the 2, and you get 0.8255. All right, so that is how, again, you can use the Appendix A to find out all the different type of answers. I got one more example to go with you before we go to the next video. All right, so in example 3, it says find the z values for specific areas in the tails. We're going to find two values, one positive and one negative, that are equivalent from the mean so that the area in the two tails totals 5%, 2%, and 1%. All right, so here we go. So I need a lot of room here. All right, so it said we need to find two tails with 5%, 2%, and 1%. All right, so what that means is if we're going to find two z values, doesn't look like I have to go find the percentage. I just have to go find the z values. I have to go backwards, so I'll show you that. So two z values, and I want the first one to be 5% total of my value. So that's going to be 95% of my value. The issue is each side only needs to be 2.5% of my data. So I'm going to use that table, and I'll show you how to do that. But I'm looking for the answer of 0.0025. This is what I'm looking for. And once I find the negative version, then the positive will go with it. So let me switch. So 0.0025 is what I'm looking for. So here is my Appendix A. And I'm going to go up until I kind of see it. All right, so here's 0.0025. Oh, went too small. It's 0.025. Yeah, so I need to go a little bit bigger. It's 2.5%. That's 0.025. My bad. So 0.025 is what I'm looking for. So for 95% of my data, I need just 5% in total, which will be 2.5%. And then this right here will convert into 0.025. So that's what I'm looking for. I don't know if I wrote that the first time or not. All right, here's twos. I'll find it eventually. Ah, there it is right there. 0.0250 is right here. So that means my z-score would be negative 1.90123456. And so if this is a z-score on this side, that means my other z-score will be positive 1.96. So this will be for the 95 percentile. You need to know this. Right now we're looking for it, but in the future, this is the answers I'm going to be just flat out asking you. All right, this next part, I'm asking for 2% of the data. So that would be 98% of my data. So if I halved that, that would be 1%, which will come out to 0.01. So now let's look for that. 0.01. Man, it looks like it falls like right here. I think this is going to be the closest one I would get to 0.01. So I'm going to use this data right here. So that's going to be a z-score of negative 2.30123 right there. So negative 2.33. And if that's this answer, my other side would be a positive 2.33. So for a 98%, you need to know that's a z-score of 2.33. 95 is 1.96. The last one you need to know is the 1%, which is 99%, which is 0.05% that's in between. And that, oh, not bad. Hold on. 0.5%, which is then 0.005 as a probability curve. So when I come over here, 0.005, this is going to be the closest, I think. The 9 will tell the 4 to be a 5. This is already too great. So this will then be a z-score of negative 2.5. What's that, 9? So this would be 8. So negative 2.58. And therefore, the positive version would be positive 2.58. So again, this one you also need to know. So when I'm asking, hey, what is the standard deviation at 95% of my data? Then you know it's 2.5% on each side. So the z-score is 1.9 plus or minus 1.96. If I'm looking for 98% of my data, then you know that's 1% on each side. So that's going to be a net plus or minus 2.33 standard deviations away. And if I'm asking for 99% of my data, then you know that's 0.5% on each side. So that'd be plus or minus 2.58 standard deviations away. All right, and then that will pretty much wrap up from there. On the next one, we'll do some actual applications now that we have a better idea of our normal distribution. Until the next video.